Today we start with process design kit overview, and I have with me Indu Bala and her co-presenter uh, Vandana. Indu and Vandana have been with NXP for over 10 years, and they have been working on the PDK development for well over a decade. So Indu and Vandana, please. We'll also be recording this session. If anybody has any objection, please let us know. Okay, over to you, Indu and Vandana.
Thanks, Akhil. Hi, everyone.
Thank you, Akhil.
Welcome to the first session. So let me start. So today we will mostly be talking about process design kits. Before we start on process design kit, we'll just give a brief overview of the VLSI design flow and also some of the terms that we might be using, and you must have already heard some of those terms, which are, always being used during a PDK or process design kit development.
Indu, can we record this session? Or it's already recording. Thank you.
Yes, thank you. Okay, so this is just to give a brief overview of VLSI design flow, and also, to tell where PDK plays, important role during the flow. So, as you know, the flow starts with logic synthesis, where you have your, net list, and you synthesize the net list, and eventually you get an RTL with the library and constraint file, and the final output is basically a circuit net list. Now at logical synthesis stage, also, however, it looks like, the PDK is not required, but when you convert that to logic gates, so for process design kits, I'll be using PDK, okay, just to avoid any confusion. Yeah, so for the logic gates, that you use during your logic synthesis, to develop those logic gates, you need PDK. Then from logic synthesis, we move to the physical design, from floor planning, placement, clock tree synthesis, routing, GDS, and finally to the chip tape out. At most of the stages, for different components, you need PDK, because PDK contains, you have PDK is basically your basic entity to start the design. It contains all the primitive parts which are necessary to start a design, whether it's a digital design or primarily an analog based design. Definitely in analog based design, it is more prominent that you need a process design gate, where in digital side, you need a technology lab and other. So you go to the physical design, where you convert your netlist by logical synthesis to a final GDS, which you send to your foundry. Yeah, I'm not going in detail of the VLSI design flow. We already had a session in October 2020. So yeah, in NXP Campus Connect, you have detailed presentation available over that. So floor planning, you decide, how your overall chip would look like. You do your, planning, how would you place your like standard cells, memories, analog blocks, digital blocks, IO cells, power planning, etc. And during the placement, you actually decide, at what location you are going to put up these circuits in your on your chip or on your IP. Then clock tree synthesis is mainly to check the top, make sure your clock is basically balanced in your circuit, and you take care of all the critical paths, and make sure that you have a minimum skew power or noise in your circuit. Routing, typically there are two stages for routing. Routing is basically doing connections within the circuits based on constraints that you define during your circuit design. And it's in two stages. You have global routing and detailed routing. Global router, what it does, it reads your design, and it creates simple blocks, or we call it tiles, where it try to find the most optimized path that can be done to satisfy the connections. Wherein detailed router takes the final. So global routing typically takes more time, it has more number of iterations, right? Wherein detailed routing will take the optimized data from global router and provides actual connections within the design. And then once your design is ready, then you go for ECOs, where you do some iteration. So these are you have multiple iterations between this these steps, and definitely there are many more steps that you do when you go for actual design. This is just a top level overview. So you create your final layout, or you dump a GDS file and you send the GDS file, or you prepare the GDS file to be sent to the foundry, and where they start preparing mask for each layer. And then multiple steps are being done in the foundry for fabricating that particular chip. And that's how you close on your VLSI design flow. Post that, it's all testing. You get your silicon and you start testing and everything. So there is just an overview. And
फर्स्ट क्वार्टर तो बोल जाओ. मैं कह रहा हूँ बोल जा तू, नहीं बोल रहे.
Guys, can you keep your mic on mute? Thank you. Some of the important terms that we use during the PDK development, fab or foundry. As I said, PDK is the first entity for any design, be it digital or analog. So PDK works as a connection between the foundry and the design team. So it gets the data, all the data defined by the foundry, and it makes sure that it provide all the rules and guidelines that the design team need to be follow to make sure that your products is manufacturable, right? And you get good yield and other stuff. So foundry, I think most of you know, foundry is a place where the actual IC manufacturing is being done. Process team. So process team, or we also call it device team or the technology team. Their primary focus is on understanding first thing about the device physics. So you need all the primitive devices to create your design. You need all the MOS, gate, MOS, resistor, cap, and inductor, other devices. So how do you develop these devices? So these are the team which work start with the basic device physics, develop your device, and work with foundry, with different test vehicles, and make sure that these devices are manufacturing and they behave as intended. So these are the teams which work on device structure. And also they work very closely with foundry, defining rules for a particular process. So they are one of the key input to the PDK team, because eventually the devices or the technology rules are being delivered through PDK. Design enablement is our group where in NXP we work, me and Vanna both. We are part of MCU and MPO engineering business line. In design enablement, so we create PDKs, we create IO, standard cells, memories, and also we work with different EDA tool vendors also. So design enablement group in NXP provides a bundle of what we call as deck, design enablement configuration file, to all the design teams across NXP, to design their products or IPs. Yeah. So we are the people who work on all these basic blocks. When we say design team, for PDK team in NXP, design teams are basically direct customer. So we work with different BLs for all the technologies, and PDKs are sometimes being customized as per the product requirement, right? So we work like, for example, if we take a 180 nanometer general example. So there can be different kind of product, RF or non-RF based or maybe NVM based. So those kind of things, so the design rules and sometimes the devices need to be customized in the PDK. So design team defines what are their product requirement, and PDK works with the technology and other stakeholders to make sure that they have everything to start their from start to finish their design. DFM is the design for manufacturability. These are basically rules or guidelines provided by foundry, and also sometimes within organization based on the learning from different products, on the yield analysis and all. So some of the rules are being defined. The DFM rules defines that the product is manufacturable. So DRC, when we go for design rules, basic design rules of foundry, those are the minimum requirement or the minimum conditions that you have to fill. But sometimes based on what kind of design it is, you need to go for the DFM rules. DFM rules are typically provides little more flexibility, but it also takes care that your area does not increase manifolds. So DFM is more like recommended guideline to improve the yield and manufacturability and also the reliability. So PDK does work with foundry and also with internal stakeholders within DE and also with different BLs to define these rules. Similarly, Esd electrostatic discharge. So what is the electrostatic discharge? Basically, when two charge objects comes in a close contact, sometimes there is a very sudden flow of current. Normally, in the input output periphery, there are higher chances of ESD issues where your dielectric can break down, or say your circuit can break down because of sudden rush of the current. So in PDK, we provide specific, components which can be used, during design of your input-output blocks. So those are special devices. Typically, yeah, they have some ESD protection diode or capacitance periphery around these most devices. Then on sign-off. That's a very common term, not just for Pdk, but I think across any semiconductor industry. When we say sign off, in terms of Pdk, what sign off means. Can you still hear me? I see a network issue.
We can hear
you.
Yes, we.
Sorry, I had a network glitch. Can you hear me now?
Yes.
Yeah, we do.
Yes.
Okay. Thank you. Okay, so coming back to sign off, the sign off means, in what conditions you can tape out or send your final GDS to design team, right? So when you have done the final routing and optimization, right? So you run certain checks. These are the design rule checks, right? And sometimes the DFM checks, and also we have sign off checks for other things also, like for reliability you have EM sign off checks, or LVS, what is your QRC sign off, not QRC, sorry, extraction sign off. So you have different sign off checks that you need to do before you take your GDS to the foundry, right? And these sign-off checks are something which foundry provides a guideline that these are the minimum checks that you need to follow, and if you deviate from that, you need to take a waiver either from foundry or from your technology team based on what kind of waiver you are taking. before going for tape out. And if required, then you do the incremental fixes, and also, the retesting is required every time you do change after your sign-off check, right? Sign-offs can be, as I said, sign-off checks can be in different categories: front-end sign-off or back-end sign-off. It depends at what stage your design is. Silicon alignment is something that is usually done by the foundry. It is about how you accurately place your different layers in an IC. So during the fabrication, foundry uses a different self-aligned process to make sure that masks are placed properly during the wafer creation. Also for test engineering, DFT, which is a common term used by in VLSI. So DFT tests are carried out, and once your design is fabricated. However, some of the test structures are created beforehand and are part of your especially your test vehicles, or also sometimes on the final products, some of the DF design. So these are the designs which are specifically created to probe into the circuit and test the circuit at different levels. Silicon validation: once you carry out your tape out, then you get the silicon from foundry, and then different kind of testings are being done to check if there are any bugs or issues. And there's a whole bunch of people or teams who work on silicon validation. They have predefined what are so they compare the specs which are for a particular design, and what is the outcome of that particular design. So if you find certain bug or issue in the silicon validation, then you go for retape out of the particular product. Okay, so yeah, now we'll start about like PDK in detail. These are some of the terms that we had used for the PDK. Now, what is Pdk? As I said, Pdk is something that you need to design your blocks from RTL to GDS2 flow. Pdk includes a lot of things. Primarily, your primitive devices, which means your MOS, capacitance, diode, resistor, inductor, all kind of your basic devices that you must have read in your device physics. Those are being provided by Pdk, and end-to-end support for devices are provided, which means how you your schematic views to your layout, the models, how it should be netlisted. The complete flow has to be there for the device, and how it should be extracted, or what has to be done in during LVS or DRC. So, and we have models, the SPICE models, which are provided by Foundry. We have design rules, different kind of design rules, DRCs, DFM. We have ESD specific rule. We have latch-up rules. So yeah, we'll go in next slides for more details about these. Then we have process info. That is something, what is a process info means how your device will behave when it is being manufactured, right? Or how your circuitry will behave when it is manufactured. So Foundry provides, the process data, which we use for extracting the device, and also for the SPICE model for pre circuit level simulation. And the extracted data, or the process info that we get, we also use to extract the device using different extraction tools provided by foundries. And yeah, based on that, we predict what is the outcome of our device. And because this process data is provided by foundry, how how the whole fabrication or how the layers will behave once they are in chip on chip, how device will behave when they are sitting next to each other or on top of each other, or at what part of the die the device is there. Also multiple scripts are being provided based on the design team requirement. Yeah, as I said, PDK can be very much foundry and process specific. If the foundry is different, then definitely not the same PDK will work, because every foundry has its own guidelines and rule. Though we say for a particular technology node, some of the basic rules may be same, but it depends on how the foundry is fabricating and also what kind of process they are using. So yeah, it is, and here the process means whether it is like as I said, it can be an RF or non-RF process in simple terms. So it is very much specific deliverable. Every foundry provides a basic PDK for every technology and process that they are supporting. So you can use the PDK directly from foundry, or there can be a customized PDK, and that varies from organization to organization and also from product to product requirement. Right? As said, as the technology is advancing to lower nodes, the PDK complexity increases, because we are going to smaller geometry, not just for smaller geometry, by different patterning and everything. So PDK complexity increases in terms of especially in terms of how the device layouts are being created, or how your design rules are defined, or how you do your LVS and other comparisons. So with every time you go to a lower node, yeah, the PDK complexity does increases multifold. Yeah, and the last point here is, for PDK, it supports the reference design flow. What is a reference design flow? For every design team or a design group, they follow a certain, design flow. For example, you have a journal with, let's say, design flow. You use certain tools inside that flow, right? Or use go by a certain way, you use a certain net listing process, or what is a different combination every design team flows. So PDK's intention is to support those reference design flows for the product that it is being created, but PDK should not dictate the reference design flow. So if the design team need some variation or some update, or they want to do things in a different way, then PDK always need to adhere to that and support those flows. So in general, in your design flow, these are some of the steps where you need your PDK. You need a PDK basically. So from specification to architecture, yeah, at this time you do not need a physical PDK, but you should be clear, yeah, right, which foundry or which node or which process you are going to, because based on that your design architecture or can vary a lot. So as soon as your architecture is defined, PDK comes into picture, and as a PDK team, we start working with foundries, to collect all the data. As I said, the base PDK is always provided by foundry. Most of the cases, the exceptions are only if you have any in-house, processes. Otherwise, you get a basic PDK from foundry. Then you go for the schematic creation. At the schematic creation stage, from PDK, you use your primitive devices, and you use the SPICE models that foundry provides, to create your schematic and run circuit level simulations. The next stage, and then for timing evaluation, you use some of the SPICE models which are part of the PDK. Then for layout, you use the parameterized layout which are part of the PDK. You use the design rules. the guidelines, the tech files, which define, your InDesign rules for creating a layout for that particular foundry or technology. Then we have a design rule check. Pdk provides, all the decks for that, and Pdk defines along with foundry and other stakeholders, what rule need to be followed for a particular, Pdk. Layout versus schematic. Pdk does provide the LVS decks for same. So Vanna will cover in detail about these decks. Then for post layout simulation, after your layout versus schematic comparison, you extract your device using the foundry provided extraction deck, which contains the process info and the design rules, which defines for example metal to metal, how much for example within a particular spacing of metal, how your caps or res will differ for a particular geometry. So that is defined by foundry. So you use that extraction deck, and once that netlist is available, we go for the post layout simulation with that in combination with the spice models. And yeah, then we go for area and timing closure. We go for different reliability checks where Pdk also provides, the EMIR decks. Then, once that is done, you go for packaging update, wherein Pdk provides the packaging deck in combination, as per input from foundry and also from in-house packaging team guidelines based on their, analysis across different products over the years. Then sign off Drc LVS. So the decks comes from the Pdk, and the design team runs these decks before they tape out to the foundry. Now for mask tape out to layout GDS file, here Pdk provides some RTO checkers. Basically these are the revision tape outs. They need to check if they have already done some tape outs, what are the differences, or if they have done all the sign off and everything, then whenever they do the changes, what kind of which mask layers are basically updated or being touched upon. So as I said, from almost every step till you deliver your GDS to the foundry, Pdk plays a very important role, and especially on the analog design and also at the SoC level, you need Pdk to go through these steps. So as said, Pdk does come, every foundry provide a basic Pdk, right? And apart from that, so these are some of the inputs that is needed for the Pdk. We have, so we have spice model for connectivity and other information. We have LVS, and also in technology file we have parameters. We define what kind of for every device, and what kind of parameters or attribute need to be used to. So these are all from circuit design point of view, all the inputs, what kind of topologies, devices which are being part of Pdk that should be supporting. From CAD side, as said, two teams can, referring to the same Pdk, but can be using a different set of tools from different vendors, so that need to be supported in the Pdk. Also, the reference design flows, if there are multiple products associated with Pdk, then you need to support, those flows that, they use. What are the target architecture of the Pdk and different configuration. These are some of the, these are some of the inputs that come from the design team, and also some of the design enablement team in NXP are also working on that. Then the design rules, right, and the packaging and everything are being defined by, what is the design intent or style or designer preferences. Over the year that I have seen that, every design team likes to work in a particular way, even if they are, using multiple technologies or, multiple process. So yeah, that also goes into input. Then from foundry side, the basic input which is required is, what are your mask layers, which defines, basically at the design side, if you see, the design cost is defined based on, what kind of mask layer combination that you are using. Mask layers are the layers that gets fabricated. What are the litho rules, which define the manufacturing or hotspots, that you may get, during the fabrication. So this is all different kind of, requirement which is coming from foundry. Multi-patterning is coming for, if you go to the lower nodes, lower than 28, then, you see different multi-patterning kind of requirement. Then basically you need layers, vias, grids, constraints. These are all coming from process team. So this is just some of the inputs, basic inputs which are required to start any PDK, right? Sorry. PDK development flow. So as I said, so we get these inputs. These are the specification which is required for PDK creation. We need a design manual. A design manual is something which defines, what are these rules, right? And then the actual rule definition, right? We also need the device specification, which need to come from the process or device team that we have discussed, right? And based on that, we create those devices in parameterized form. Also the model specifications. Model specification are typically, defined by the design team based on, what kind of process they are using, and then we can, within the PDK models are sometimes a part of PDK, and sometimes it is outside PDK also, but it is a very important, attribute to the PDK development, because model specification also defines how your device would be netlisting, right? What kind of parameters you need to netlist in your design, or when you are doing extraction, then what kind of layer should be extracted or what should not be extracted. So those kind of specifications come from model. Then LVS specification needs on, what you want to compare when you are comparing your schematic versus layout. And the test specification, how you want to test your PDK or overall devices or the integrated flow of the PDK. During the development, yeah, these are some of the things. There are other attributes also. We create tech file. There are different kind of tech files. It can be a tool specific tech file. It can be a DRC tech file, which are, we also call it like rule decks, like DRC rule deck, LVS rule deck, EMIR rule deck, or electromigration, rule decks. So different kind of rule decks, or you can have like your left files, technology left files. Then you have design device data format container, where you create you are creating here your devices, right? So you're creating your net listers, or you're providing all the front end information for the device, what kind of parameters netlist, or how it should be netlist, or what is the device information. Then PCell, apart from, see, tech file and PCells take most of the time for PDK development, because they are the most complex items, and need lot of iterations and testing before we deliver the PDK to. PCells are the parameterized layouts, where it can be in different structures, right? It can be a simple layout, one fold layout, or it can be a hierarchical structure. The requirement come from the design team, what kind of devices, and also from the technology team, what are the basic devices that should be part of your PDK. Once that is done, the testing side, we do the integration. So first we do the unit level testing for all the components, which is like, so here it's on a DRC, LVS device models, or IPs. So we do all the unit level testing for all the component, and then there is the integration testing being done, especially for all the devices which are placed. So you can create a common test case using all the devices, and then you make sure that the run flows fine, and you don't see any issues during DRC or LVS or extraction or simulation. So there are a lot of manual testing is being done, and there are a lot of automated test suites that we have created. within the PDK team, which makes sure that once the PDK is out, it is of good quality and can be directly used for production version. IP test, we do run a lot of IP, we call it IP regressions. So IP tests are being performed once at least one version of PDK is available. So if, for example, if there is a 1.0 of PDK is available, so next time when 2.0 comes up, we take the input from different design teams. We take their IP blocks and we run regression testings as compared to the previous version of PDK, to let them inform in time, what kind of changes they may observe when they move to the next PDK, and whether those are the mandatory changes or those are the recommended changes. So that's a general flow for the PDK. Okay, this is the last slide for me, and then I'll hand over to Vanna. This is about Pdk output. As I said, we get input from process team, design team, foundry, and from different other stakeholders from our packaging team, maybe Esd team, DFM team. But at the end, this is what we deliver from the PDK, right? Once we have all the inputs, we compile, we create our rule decks. These are the basic outcome which you will see for each and every PDK. There may be other components also, but that depends, that would be very specific to the PDK and also for the design requirement. So DRC is your design rule manual. Then you have LVS layout versus schematic rule deck. PEX is your extraction deck based on what tool you are supporting. Then different mask for mask layer information. You have GDS2 map files, the OSS map files based on what format is supported. Then from process side, we have layers and vias and all the tech file definitions. We have tech file left, is library exchange format. This is also one of the way to generate the tech file for particular tool. Also, all the tool related tech files which is required when you create your design. What are the basic or in design requirement when you create your layouts specifically, right? You have design rule manual which provide all the guideline rules and everything. So before you go to the DRC, you can also check the design rule manual for basic guideline. This is the validation, so which provide what kind of inputs or regression that we have done, especially for IP regression. It is very important. Then on devices side, we provide different parameterized cells, symbols, their callback, P cells, everything. And on simulation side, multiple views. So you need stop views for every simulator, based on what simulator or from which vendor you are supporting. So every vendor needs a different simulator view. Also, sometimes you need to have a separate netlister for different vendors. So we create those netlister, also part of the PDK, the tool interface on whatever simulation tools you are supporting and the models. Yeah. So these are the more or less on top level, the PDK deliverable. So thank you. Now I'll hand over to Vanna. Vanna has expertise in extraction and EMIR domain. Vanna, over to you. Thanks.
Yeah, thank you, Indu. Thank you for that details and the overview. So I'll just take the screen so that I can move cursor myself.
Sure.
Just a minute. Okay. So is my screen visible?
Yes, it is. Yeah.
Okay. Yeah, so going over to the different PDK, we have the different, one part is the PDK process constraints and then the device. So by the process means it has the information about the different, the process specific information for all the mask layers and vias. So when we go to process the foundry, there could be multiple metal layers or via stack in that process, which include the specific foundry specific processing also, like it could be a bulk process or an SY process. So all those details are captured in the various rule decks that the foundry provides us. There's also technology specific information for each layer, like their the what are the resistivity, what are the different backend parameters, etc. We also have the reliability information, like the rules that dictate whether these metal layers what sort of current limits that they can sustain without falling apart. And then there could be different tool related support information. So different map files, different collaterals for multiple tools that are available and supported through that PDK. The design rule for fabrication. So what are the rules which are required for foundry to be make a product manufacturable and good yielding. And likewise, on the similar lines, their PDK also contains device information. All the devices that are part of the PDK, which are the resistors, capacitors, BJT or MOS. And the device structure, as we already discussed, that we have a process team which is more like reviewing the device with respect to its physics parameter, and also with respect to the feasibility, that means manufacturability, and behavior means the performance. So all these aspects should be looked after before we decide on a device structure and we implement through PDK. And on same lines, the PDK also support these parameters, like what are the parameters which are required for the designer to play with, whether they want to have what kind of width, length of say MOSFET they want to play with, if it's if it's a different device, what all additional parameters are required. And likewise, those parameters pass through all the stages of front end, like symbols, callbacks, and back end through layout. They all come into this category, and they are so all supported through this PDK different views, layout views or symbol views, etc. Going over to the DRC part of it. So when we talk about DRC, our main input is the layout. Layout is the different shapes we have in our design, and the how we put across different metals, different layers. It also defines how it manufactures in the fab. And to make it really manufacturable, there are multiple checks that are available through PDK. One is this layout versus schematic. So the schematic you can think of as a design intent, and the layout you can say as implementation. So the intent must match the implementation for a design to be complete. And also the design rule check, which check whether you have specified the correct dimensions for those polygon shapes. And antenna rules, they also tell that whether there are no antenna effects or issues during the fabrication process. Likewise, there are packaging and parasitic extraction models are available. These model tells what would be the extracted output and whether those parasitic are okay for the device performance, or we are going beyond those performance specs. Likewise, for the DFM part, like design for manufacturability rule decks, they also decide how the design will be manufacturable, and these rules help to get the more process friendly layouts done. When we are talking about the rule decks, there are multiple rule decks for each of these components. By component, I mean the different engines or different collaterals of PDK, like LVS, DRC, extraction, and so on. And these rules are meant to ensure the functionality and manufacturability and reliability of all these of the design and the in question. So basically, the when we have these all these rule decks in the PDK, they are all technology specific and foundry specific, because different technology node may have certain additional rules, like you are on a different double patterning process, or you are on the regular process. So based on your specific process, the rules are also aligned to the foundry how they are manufacturing it. Also, the mask information is a input that is required by the PDK in form of the GDS2 or the OA layer maps. The layers that are constituted in the PDK, all the metal layers, the BUL stack contains the layers and their this GDS2 and the data number information to further analyze this data. And there are also certain marker layers or dummy layers which are used. Marker layer used to have a certain functionality of LVS to check on certain device formation. And dummy layers are more like fill layers which are required for the better manufacturability. The design rule manual is one of the inputs which is actually tells all the guidelines for every rule in the PDK in text form or the pictorial form. There is also a metal stack information. So by metal stack, we mean like, what all metals constitute that process, whether it's a 5 metal process or 7 metal process, and how that stack is constituted, what are the layers involved, and the details. There is also, it also contains the reliability information in terms of the EMIR rules, like, what are the allowed current limits for every metal layers, and what are the different rules to be checked for the EMIR. There is also as part of the DFM, there are also mandatory versus recommended rules. Now I'll switch to bit over the details of why DRC is required. So DRC is required to have a manufacturable die. This manufacturability requires that the device that is intended has specified dimensions which are allowed, and the devices are formed properly. There should not be any shorts or opens or antenna effects during the manufacturing of those designs. And also the reliability is met. There are no dielectric breakdown or those kind of issues that happen during the fabrication. We also have a very big impact in terms of if a single DRC goes undetected, the whole design need to respin, and it cause lot of loss of market, or the product profits will really sink. So this is really crucial to have a DRC clean design, and must for the high yielding or the manufacturing of the process, because unless we have a good number of functional dies per wafer, the those product will not be much high yielding, and definitely it will hurt on the fab cost or the profit margins to make those wafers. Now going over to what all the basic errors are checked in DRC. So these are the like, we have the spacing checks which are caused by the unconnected geometries, like different metals which are spaced a certain distance apart. There could be notches on the same geometry. There could be a notch formation. There could be a minimum size, like some geometries are beyond a certain minimum size, and also the resolution, like what is the layout resolution, so that the geometries are not beyond a particular limit. Now this is a different like, checks could be written, like, this is the width. So you have the distance between the inside edges of a layer. So we can specify, the rule may specify that this is the minimum width of a particular polygon. Likewise, when we talk about space, we could have a same polygon or same type of metal, different polygons far apart, or we could have different layers which have we are trying to check spacing. Now the notch is on the same shape, but it's external edges, distance between the external edge pairs on the same layer. And overlap, as we can understand from the name itself, it's a common area, and the inside edges, distance between the inside edges of these two shapes. When we go through these different DRC rules, then there's a basic flow to it, like the rule deck forms first takes the input as original layers, like you have different mask layer, active, poly, and so on. So those mask layers are taken as input, and there are Boolean operations performed over them, like for example, this is an OR operation. You have a derived polygon layers, and then there could be certain checks written on top of them to derive the edge layers, and then also the error layers, like the minimum distance between these two edges has to be a certain minimum number, otherwise it will be flagging as a DRC violation. This is also depicted through the flow diagram here, that we have a layout database which is provided to the DRC deck. These original layers are taken and the layer operations are done. And then the output is derived polygon layers, derived edge layers, or derived error layers, and they are outputted to the DRC result database. This is shown through this. This is the function where the Pdk comes in with the DRC rule deck, and also there are certain tool support features might be part of the Pdk, and this is the output which the designer will see on their once they use their layout to go through the DRC checks. After going over the DRC, the designer typically goes for the LVS, means that they want to check whether their intended functionality is implemented on silicon. And by intended means that they have a schematic available which has certain specifications, that it should have the current through it should be this much, or the the maximum current, or maximum drive, the threshold current or saturation current should be this much. Those features are in the schematic, and then they have a layout. So suppose they have in the schematic side they had an inverter, but layout side has a buffer. So LVS will check and tell that the design intent is not matching what is present on the layout, and it will also ensure that there's no shorts happening or opening in the design. Could you please mute? There's still sort of noise here. So basically, when the LVS is running, it is checking for shorting or opens also. So certain nets may short together, and then it will destroy the chip functionality, like a power ground short, or certain there may be certain opens, and those opens will lead to undesirable outputs. And after checking that, suppose we get a match, everything is aligned, the schematic and layout are aligned, then we are good to go for the parasitic extraction. And as output, this LVS deck also provides annotated net names annotated with the net list to proceed for the parasitic extraction. And after parasitic extraction, these the netlist will also get annotated with the RC data. So as we went through briefs of the LVS, for a particular node, the foundry provides set of rules for recognizing the devices, and it also provides the LVS deck also provides a connectivity information through the LVS deck. These rules define how to derive devices and the interconnect nodes, and also attach names to the extracted nodes. So the netlist, if the input has VDD, VSS nodes, then the output netlist from the LVS will also contain those extracted nodes. And then The extracted circuitry is compared with the reference to make sure that it is correctly placed on the layout. The typical flow of LVS is you have a layout. It goes through the connectivity extraction, and then the device recognition part is like that we saw that we could have a MOS or BJT or inverter, etc. Whatever on the devices on the present in the layout, LVS will recognize those, and then it will compare with the schematic to tell you the report, which will be the result will be either match or mismatch. And as part of the comparison, it also need a source netlist, which is a source spice netlist. This is also needed for the comparison purposes. After you have gone through the LVS stages and your design is a clean LVS match, we designers go for the extraction part. And the extraction part includes both the information about the parasitics, which are the RLC parasitics of the interconnects, plus the devices that are present in the layout. And over the years, as the technology has shrunk, more and more, interconnect delays are dominating over the gate delays. And the parasitics are much more critical for the design tape outs and performance. In the previous slides, I think when we were walking through the RTL to GDS flow, we saw that there were a lot of steps which included in the physical design going from RTL to GDS stages. And those all those stages require the process of extraction, where we have multiple checks like EM checks or self heat analysis, timing analysis, IR drop analysis, or crosstalk analysis. And all these are actually meant to catch what all issues we see in those design cycles. So, like for example, if the parasitics are much large, they could give rise to large power consumption, and the power specification may be violated. So, it's important to run the EM checks. Likewise, much high power consumption on the dyes could also trigger increase in the local temperatures. So, self heat analysis is required to be done. If we talk about timing, they are very critical for all stages of the physical design. So whenever there are timing violations, the STA needs to run and to check the physical net list at all stages, and then any iterations in design need to again go through this STA analysis and fix the timing violation. So delays, timing, parasitics, they all come through the extraction part. If we also have the IR drop analysis. So the power rails, or you can say your power rails could be causing a lot of IR drop. So the design, when the designer is doing the physical design flow, they have to constantly check whether the IR drop is acceptable limits, or the design will function, or it is too much that the design need to be tweaked to get better IR drop performance. And all those checks are carried out through the PDK collateral. And likewise, as you know, the crosstalk, if it is too high, the signal may get, the signal may be incorrect signal may process, and the logic failure may happen. And all those things are actually impacted by the extraction performance. Now, when we talk about extraction, usually the foundry provides some corners for extraction, and the corner for extraction are based on the due to the different type of variations that are happening on the during the fabrication process. So we know that there are the part of the fabrication is CMP, like chemical mechanical polishing, and during this process there's also erosion and dishing effects, and that's why there's density checks etc happening during the DRC stage, and this is also those variations of the interconnects, like some metals may be close apart or far apart. All those effects are modeled in the interconnect decks. Likewise, metal thickness as a function of density and width, this is also modeled through the extraction models, and resistance dependency on line width, um, or the OPC effects, they are all modeled in the through different extraction tech files and for different corners. The random variations are could be due to the various reasons during the manufacturing, and they also lead to the changes in the geometry or the properties of interconnect. So all these different effects, like process effects, are captured through the extraction tool in the extraction tech file, and designer, when they run their extraction, they can see their design, how it is performing, and do the checks that we just elaborated. Now, the extracted netlist for a custom design flow generally goes through the simulation stages. And here, what we the PDK uses the SPICE models and for the simulation, and interconnect models actually tell about the interconnect delays on the design. The part of PDK, there's also electromagnetic simulation that is supported through PDK. So this is your EM tools, and also the EMIR, which is the electromigration analysis. After doing all these different stages of development of the devices, we go for the detailed PDK qualification. And the PDK qualification, the first part is the all device testing. All device testing means all testing all the devices for all these stages: DRC, LVS, PAX, simulation, etc. For the on through the common test case to check all these collaterals. When we talk about the PDK qualification, there's also another part of IP regression. So herein the different PDK versions are compared, and the design IP is picked to compare the results of DRC, LVS, or extraction for the different versions of PDK, to make sure that the designer is their test cases are still working as intended. There's also detailed unit level testing through the QSL. So basically, DRCs are mainly targeted for this unit level testing, where a good or a bad test case is created and checked for the DRC rules. There's also automated test suite, which has certain internal tools that they generate the test cases and check for the PDK collaterals. There's also a flow level testing to validate the different tools and flows that are supported through PDKs. Like we have the there could be different vendors that are supporting the same LVS. So those are the tools, their tool support and their seamless flow is tested through the flow level testing. And the integration testing is like the complete the the complete package as it is going out to designer. It is working fine. So all these aspects are covered during the PDK qualification, and that's pretty much covers the details of the PDK.